Okay, so today we are working on lesson 4, points of inflection. And we have talked a little bit about a point of inflection when we first started looking at the first derivative and extrema. So we're going to just analyze that a little bit more today. So the first definition we have here is a point of inflection and the second derivative. So a point of inflection is a point where the concavity of the curve changes. All right, so simple, simple, simple. In the simplest form, we are talking about where the concavity of the curve changes. At a point of inflection, the second derivative will be equal to 0. We've got two examples there. We've got a stationary point of inflection, which would be this one, and a non-stationary point of inflection. So let me explain what I mean by the difference. So if we're talking about a stationary point of inflection, which is something we have already examined, we know that the first derivative is equal to 0. And it came up because we were looking at the first derivative, we were setting it equal to 0, and we were trying to decide, do we have a minimum, a maximum, or a point of inflection? So if a function was continually decreasing, like in this example, right? It wasn't a minimum or a maximum, but it was a critical point. Something was happening to the graph at that point. So at that point, we have a change in concavity. Or we had the scenario where it was increasing and increasing, right? And at that point, we had a change in concavity. So on this guy, we went from concave up to concave down, and here we went concave down to concave up. So at a stationary point of inflection, the first derivative is equal to 0, and the second derivative is equal to 0. At a stationary inflection, the function is neither increasing or decreasing. Right, so right at that point, if you were to look at the derivative, right, the derivative at that point, if we were to draw, remember the derivative is the slope of the tangent line. Here's the tangent line at that point. The slope at that point is 0. The slope at this point is 0. So the first derivative equals 0. And the function at that particular point is neither increasing or decreasing. Now, if we're talking about a non-stationary point of inflection, the second derivative is equal to 0. Notice that's a little different from stationary. We're going to have the first and second derivative equal to 0 for stationary inflection. Right? For non-stationary inflection, only the second derivative is equal to 0. And at that stationary, well, it should say non-stationary, a little note here. At the non-stationary inflection, the function is either, it will be either increasing or decreasing. All right, so you notice that we have a decreasing slope here. And on this graph over here, we have an increasing slope. We're increasing. We have a positive slope and we have a negative slope. And I really like this summary at the bottom of the page. I mean, it kind of gives you a nice look at what we're talking about in terms of the first derivative and the second derivative. So the first derivative equal to 0 includes minimum, maximum, and stationary points. And when we get into the second derivative, we are going to find our non-stationary inflections. All right? So let's take a look at some examples. The first thing that we're going to do is find and classify any points where the derivative is equal to 0. So we're going to find the derivative. And then we're going to set that equal to 0. I'm going to factor out a 3, and we're going to solve for x. So in this case, we get two critical values at 3, at x equals 3, and at x equals 1. So we're going to mark up our sign diagram. And we're going to look at test values for the first derivative before 1, between 1 and 3, and after 3. If we put 0 into our first derivative, we're going to get the value of 9, which is positive. If we put 2 into our first derivative, we're going to get a negative 3, negative. And if we put 4 in, we will get 9. All right. So it says find all local maximum and minimum. So we have two scenarios here, right? We have increasing to decreasing. So let's draw that. We have increasing to decreasing, and that's happening at x equals 1. And then the other scenario we have, right, is decreasing to increasing. So we have decreasing, to increasing. And that's happening at x equals 3. So you can tell, right, we have a maximum at x equals 1, and we have a minimum at x equals 3. So we know we have a, I'll just write a note here, max. We have a min. The max is happening at 1. The min is happening at 3. Now it says find the intervals where the function is increasing or decreasing. We've already identified it with our sign diagram, right? We have increasing, decreasing, increasing. So we're going to write increase where x is less than or equal to 1 and x is greater than or equal to 3. Right, and it might be helpful to just make a note of what the graph would look like here while we're thinking about it, right? We're increasing, we're increasing, we're decreasing, and we're increasing. So we have a max and we have a min. So decreasing is happening where x is greater than or equal to 1 and less than or equal to 3. Now we're going to look at any additional points of inflection. We didn't find any stationary inflection points. We had a max, we had a min, but we didn't have anything in our original sign diagram where it went like positive, positive, it went positive and positive or negative, negative. It changed from increasing to decreasing and then back to increasing. So we didn't have any stationary inflection points. Now in the next example, we will, so you'll see what I mean. But we're going to go ahead and find the second derivative and see if we can find any non-stationary inflection points. All right, so we're going to take the second derivative now. The second derivative of the function is a little bit easier. All right, we're going to get 6x minus 12. We're going to set that equal to 0. I'm going to pull out the GCF. And we know we have a critical value happening at 2. So we want to evaluate on our sign diagram a test value that's less than 2. I'm going to use 0 because that's easy. That's going to be negative 12. And I'm going to use a test value after 2. So if I put 3 in there, I'll get 6. So I've got a negative and I've got a positive. That means concave down. and then concave up. Right, so the function, and we can see that if we look at the graph that I drew here, right, concave down and then concave up. And where is that happening? It's happening, the concavity is changing right at the value of 2. So we can draw a little graph here. Let's try to see what I mean here. So it's happening at 2, where the concavity is changing from down to up. All right. Find the intervals of concavity. So we're going to write concave down. That's where x is less than or equal to 2. And concave up, where x is greater than or equal to 2. Now it says sketch the graph showing all the features that you found. So we want to take any important points that we found and we want to plot them. And by the way, since concavity is changing at 2, right, I just want to know what the coordinate, what the y value is at 2 for the graph. So let me go back to my calculator. I'll store in 2 for x. And I'm going to get a value of 3. So if we go back to everything here, what are our important points? We've got, I'll do them in blue. We've got a max, we have a min, and we have a non-stationary point of inflection at 2, 3. So those are the 3 points we need to plot. We also know the end behavior because we've sketched out increasing, decreasing, increasing, examining our sign diagram for the first derivative. So let's plot all those points. All right, let's see, we've got 1, 5, 3, 1, and 2, 3. And then I'm just going to go ahead and sketch it. Let's see, I'll use, do it in blue. So it's going to go something like this. Right here is where the concavity changes, and then boom. All right, so we have a maximum, we have our minimum, and right here we have a non-stationary point of inflection. Okay, that's that example. Well, there's a lot to this, so I want you to be really patient because these take time. I mean, there's only 2 examples in this whole lesson, and there's a reason for that. All right, let's take a look at example 2. First thing we're going to do is we're going to take the first derivative. All right, and then we're going to pull out the GCF, and the 12x can be pulled out of each term. So I'm going to rewrite that and make it easier for me to factor, because I definitely don't want to factor when I'm looking at originally. All right, so we have critical values at x equals 0, right, for this guy. And both x minus 2 and x minus 2 tell me I have a critical value at 2. Right, so we're going to plot those on our sign diagram. We're going to use test values. Always pick the easiest ones possible. All right, so at -1, we're at -108. At f prime of 1, we get 12. And at f prime of 3, we get 36. Ooh, so we have a positive and a positive. All right, so the next part we're looking for minimum, maximums, and stationary inflection points. So let's just try to sketch the graph based on what we have came up with on our sign diagram, right? So our graph is going to look something like this. We're going to do decreasing, and then we're going to increase, and then the concavity is going to change, right? So we've got decreasing, and then starts increasing, and then right here, we've got a concavity change. So let's mark that up. So this is happening at x equals 0, and this one is happening at x equals 2. So notice that we're still, let me just mark this up. We've got decreasing and then increasing, so increasing. But we do have a shift in the concavity. So we're basically concave down. Right here is where we're concave down, and then we're concave up. So we want to make a note in this box. We have a minimum at x equals 0, and we have a stationary point of inflection at x equals 2. If I put 0 into my original function, I get -9. If I put 2 into the original function, I get 7. All right, and let's make note of where we're increasing and decreasing. So we're increasing where x is greater than or equal to 0, and we're decreasing where x is less than or equal to 0. All right, the next part is find and classify all the points of inflection. So let's go ahead and do that by taking the second derivative. So we're going to get 36x squared minus 96x plus 48. We're able to pull a 12 out of that. So we're going to get 3x squared minus 8x plus 4 equals 0. Now we have to factor the 3x squared minus 8x plus 4. I'm going to do it off to the side here. Use a thinner pen. So let's see, we have 3x squared minus 8x plus 4. We'll use our Kung Fu trick. We get a 12. 3 times 4 is 12. So we get x squared minus 8x plus 12. So that would work out to be x minus 6, x minus 2. Now we can do the Kung Fu part of the trick. We're divide by 3. Simplify. So we're going to get x minus 2, 3x minus 2. So we're going to add that over here. So we get x minus 2 and 3x minus 2. So that means our critical values are going to be 2 and 2/3. All right, we're going to put them in order. 2/3 comes before 2. Now we're going to use our test values and putting our test values into the second derivative. I need a value before 2/3. So I'm going to pick 0. I need a value between 2/3 and 2. I picked 1. And a value after 2. And again, we're just really deciding, whether or not we have a positive or negative value. So we have positive, we have negative, and we have positive. So what does that mean? That means we're concave up, we're concave down, and we're concave up. It says find the intervals where the function is concave up or down. Let's just note those. So we're up where x is less than or equal to 2/3 and x is greater than or equal to 2. And we are concave down between 2/3 and 2. Now we already know that the value of 2, we've already identified 2 as being a stationary point of inflection because it showed up when we took the first derivative. So the guy that we were not aware of till we did the second derivative was this 2/3 right here. So we have a non-stationary point of inflection. All right, non-stationary point at 2/3. And if we put 2/3 into our original function, we're going to get negative 2.48. All right. Oh boy, that was a lot. All right, so let's highlight everything we need now to do this graph. We've got some important points here. We've got 0. We've got a min at 0, -9. We have a stationary point of inflection at 2,7. And we have a non-stationary point of inflection at 2/3, negative 2.48. So those are all the points that we want to put on our graph. Okay, so we're going to mark it up here. I'm going to do 1, 2, 3, and we're going to need to go up to 7. We need, let's see, negative 2.48 on the y's, and we need all the way down to, say, -9. So let's plot those points and then see if we can sketch the graph. All right, so we have 0, -9. We have 2 and 7. And then we have 2/3, so right here. Now it might be helpful before we even try to draw anything, just to kind of mark what we have and, just to remind ourselves what the shape, this is what the graph is supposed to look like. All right, so 0, 9 is going to be a minimum. I'm just going to write minimum. All right, this point right here is going to be a non-stationary, I'll write non-stat point of inflection. And this point right here is supposed to be a stationary point of inflection. I really need these notes to help me before I even try to draw the graph. I'll just say inflect period. All right, so now we're going to try to draw it. I'm going to go, I know that I'm decreasing. Concavity is changing ever so slightly right here because it's non-stationary. And then I'm going to best it up. And then right here, it's a more of a dramatic, because remember, when we're drawing a stationary point of inflection, the slope is supposed to be 0 at that point. Whereas at a non-stationary point of inflection, the slope is either increasing or decreasing. So that's about as good a job as I think that I could do drawing that graph without a calculator and just using what we learned on this page. All right, so this is a lot. I realize that. And remember, these are going to take time. You're going to have to be very patient. And I think one of the great benefits of having a recording is that now you can look at this again and you can pause it and you can rewind it, and you may need to view it a couple times as you work through the practice problems. All right, so I would say Number one thing to think about when you're doing this, when we're at this point with the curve sketching, is to be patient and take your time. All right, thanks for watching. Have a great day.